Afternoon lectures are just always an adventure. You never know what's going to happen. Next Friday is Good Friday, and we don't even have class. And then Easter Monday is off. That's why I was like, oh yeah, I could have a party on Friday, and then I have like multiple days of recovery. But I don't really like to get...
What do you mean recovery? Just drink some more.
Yeah.
Just keep going.
I don't know. I've done too much of the too much drinking thing. It's not for me. Not for me anymore. I reach a point where I'm like, I'm not having fun. Why am I doing this? This is not a good time. And then I don't do it again for years. So just a few. Perfect.
So what you're telling me is you're at that point where it's time to do it again to remember.
No, I still remember it sucks. Still remember it sucks. Okay, lecture 4.1, steady state error for unity feedback systems. This is the only lecture in this chapter, so we're going to learn all about steady state error in one lecture. It's that good, this lecture, so pay attention. So, it is uncommon, so we're doing unity feedback system, so I wanted to comment on what unity feedback means. It's uncommon for a feedback system to be truly unity. So, we're going to look at one here. Unity means that the output gets fed back, and there's no transfer function in this feedback loop. So you can have a transfer function here that might not be 1. Okay? So non-unity would be if it was not 1. But we're going to only look at unity feedback systems. And you might say, wow, I mean, that's really restricting ourselves. Are we really going to run into these unity feedback systems in the real world? And the answer is no, you won't run into them. However, there is a nice way to take a non-unity feedback system and roll it into a unity feedback system and do your analysis with it. So that's what the recommendation is. There's a section in NEAS that shows you how to do it. It's pretty straightforward, but I give you the reference there in the footnote. So check that out. It's like section 7.6 or something in NEAS. Okay, so first we recall the final value theorem. Earlier, people didn't remember the final value theorem from probably differential equations. Did you guys, anybody, final value theorem? No takers? Okay. So first we recall the final value theorem or learn it for the first time. But if you're Socrates, then everything that you learn you're actually just remembering. Because how could you ever know to learn something that you didn't already understand? You wouldn't even be able to conceive of it to learn it. That's the argument. It's maybe a little bit better put in the way he does it because he's cool. But yeah. Let f of t be a function of time. I'm just stating the final value theorem. Let f of t be a function of time that has a final value, f of infinity, which is just the limit as time goes to infinity of f of t. Okay, that's the final value. Then the final value theorem says that from the Laplace transform of f of t, f of s, the final value is f of infinity, so the same thing, but instead of taking the limit as time goes to infinity, we're going to take the limit as s goes to 0 of s times the Laplace transform of the function of time, f. So that's kind of cool. You can compute the final value in the Laplace domain. Convenient. We're going to come back to that. Let's consider the unity feedback system of figure 4.1, which is the one we looked at here. Okay. You take the output, you feed it back with no transfer function in the feedback loop, so it's unity feedback. We subtract it from the command R to get the error E. We go into the controller transfer function, G1, and that puts out the control effort, which is the input to the plant, G2, which puts out the output. Okay, so that's our standard feedback.
What made it the unity feedback loop? You said no function in the feedback?
Unity feedback means there's no transfer function in here. There's no block in here. So we can always transform a non-unity feedback system to a unity feedback system, which is why we're just going to consider unity feedback ones. And if we have non-unity feedback, we can transform it to look like this. So G1 is the controller, G2 is the plant. Now, recall that we call E of t, or its Laplace transform, E of s, the error. We want to know the steady state error, which, from the final value theorem, is just the limit as s goes to 0 of s E of s. So we could take e of t, a function of time, and take the limit as time goes to infinity, but then we have to solve the inverse Laplace transform problem, which is generally hard. We don't like it. So you can find the final value without having to do that. It's kind of nice. And that's what this final value theorem allows us to do. So just take the limit in the Laplace domain. Now, all we need is to express e of s in more convenient terms. For the analysis that follows, we combine the controller and plant into one transfer function g equals g1 times g2. So you can just take these together, these two blocks, they just cascade, right? So you can take two cascading blocks and combine them to be g of s equals g1 of s, g2 of s. Yeah, so that's what we're going to do. And there's no, we could carry the g1 and g2 around, but they just are always lumped together, so we'll just put them in one. Okay. From the block diagram, we can develop the transfer function from the command r to the error e. So let's just do our usual thing where we interpret the block diagram as an algebraic description of the control system. So the summing junction always gives us an equality, e of s. I'm actually going to skip the of s. E is equal to r minus y. These are all in the Laplace domain. They're all functions of s. I don't want to keep putting of s. It just kind of clouds the notation. So e equals r minus y. And so that was this summing junction. We want to find a transfer function from e to r, okay, or from r to e, because r is the command, so it's the input, and then e is the thing we're interested to look at, so that's our output in the little mini problem we're doing here. So we need to get rid of y, and r we want to keep. Y we want to get rid of. Y is equal to, well, you could say g2u, and then u is equal to g1e, and then g1, g2 is just g. Or we could just see that this whole thing is g, and the input to it is e. So y is just equal to ge. Okay, so if y is equal to ge, we've got e in here, r, and e on the other side of the equation, so we can find the transfer function from r to e. So this equality implies that e is equal to 1 over 1 plus g times r. Or we could also say, or the transfer function is e over r equals 1 over 1 plus g. So this is the transfer function. This is the solution for e. Either one is fine. We're actually going to use this version in a second. So given a specific command r and forward path transfer function g, we could take inverse Laplace transform of e to find e of t and take the limit. So we've got an expression for e. We could just plug in r, plug in g, take the inverse Laplace transform, and find the final value, right? But we want to do a little bit more analysis because we don't know a specific g, we don't know a specific r, so we need to try to interpret as much as we can from the characteristics of what r might be, what g might be, and that's what we're going to do. So going forward from here, we're going to take this result for the error, and we're going to look at specific sort of important paradigmatic cases. Now, and certain features that show up, and what those implications arise from there. But I want to stress that you can always go back to this, and you can always say, oh, this is the error. You could always plug in for a specific case that you're working with, what r is, what g is, take the inverse Laplace transform, and you can find the error as a function of time. Pretty cool. You could always just do that. So don't overlook that as a possibility. We're going to explore some cases that are going to sort of light a path before us, like, really intense flashlight or headlamp at an adult Easter egg hunt at South Sound Church tonight, 6 to 9.
Are you promoting me?
I guess I am. Like, I don't know. I just like spontaneously did a promo there. I don't know how that went. Okay, so
Promotion.
yeah, I don't care if you guys come. You guys can come. Can't come to my party though. Sorry. I have thrown a party for students once. It was really fun. I might do it again this year. We'll have to revisit this. It won't be next Friday though, because that's already another thing. It's terms of endearment, and that would just be weird if you guys were there. I feel like it would just, yeah. We shouldn't go there. It would be bad. I don't want you guys to be that close to each other. Like, you got to focus on your school. You got to focus on school. Okay. Okay, given a specific command R and forward path transfer function G, we could take that inverse Laplace transform and then take the limit. However, it is much easier to use the final value theorem, which is what we'll do. And we see that, as we wrote above, that the steady state error is the limit as s goes to 0 of s e of s. We have an expression now for e of s. So let's go ahead and plug that in. It is e equals 1 over 1 plus g times r. So I'll put the s that's multiplying it in the numerator. So it's 1 over 1, or s over 1 plus g, which I'll put in g as an explicit function of s here just to remind us, because we're taking a limit as s goes to 0 times r of s. Okay. This last expression is the best we can do without a specific command r. Okay, we need to know what r is in terms of being able to compute this limit. But 3 different commands are typically considered canonical. So what we're going to do is we're going to just assume that our command is one of these 3 commands that we're going to use, and they'll sort of characterize the system for us. And they're going to be familiar looking functions. So yeah, we'll take a look. So this 3 different commands are typically considered canonical. The first is now developed in detail, and the results of the other 2, the results are given below in the table, and we'll look at that in a minute. So first consider a unit step command, which has the Laplace transform 1 over s. Oh, do you have a question?
I think he does, but what is canonical?
Canonical. Oh, yes. So canonical is like, in some sense, like conventional, the ones that people all agree on. It's just like the Bible has the canonical books. Well, there are a couple versions, but the Roman branch of the Christian church has the canonical books of the Bible, like Leviticus is in there. In all of them, right? Those are the canonical ones. There were some other texts floating around at the time when those got all put together. They did not get included, and like people love to fight about whether they should have been included or not, and whatever. So the canon is the ones that everyone agreed on back at that convention in like 300 or something like that. Yeah. So anyways, does that answer your question? We talked about the Bible for a minute. I like to always mix in, whenever I answer a question, I like to mix in a biblical reference, just to make sure that we're on solid footing. Okay. I need to be careful. I need to be very careful. No, I grew up in evangelical church, so I'm used to like biblical references being brought up to make every point. So I just did it there in an engineering class. I didn't think that was going to happen, but it did, because canon came into question. We never question the canon. We don't do it. It's canon. Okay. It's canon. That's right. It's like saying it's gospel. It's canon. It's canon. Okay. The first is now developed in detail. So we're doing that first one where we're going to say, okay, we're going to take one of our command functions. So in this case, a step function. And we're going to do some analysis with that. Okay. Now, the step function is convenient because it's a specific value. It's like you're saying, I want my robot arm to go to 30 degrees. That is a constant value that just persists. The step function goes from 0 to 30 degrees. So it's like saying my arm was at 0 and now I want to go to 30 degrees. But it's also like saying my arm was at 42 degrees and I want to go to 72 degrees. So it's going to respond in a very similar way, identical way, but just shift it. So any sort of step change in your command is going to be well modeled by a step input. We'll use a unit step input, and if you look that up, that Laplace transform is a nice, easy one. It's just 1 over s. So that is what we'll use. We can just plug that guy right in there. So we have our steady state error, e of infinity, equals the limit as s goes to 0 of this, so we'll put that back in there, s1 plus g of s times r of s, which now is 1 over s, right? The unit step function, Laplace transform thereof. Now, we have a nice thing happen here, right? S's cancel. I mean, nice, depends on how you look at it. I mean, you might have been like, I was fine with the s there. I didn't have any particular persuasion either way. But this just leaves us with the limit as s goes to 0 of 1 over 1 plus g of s. And remembering back to limits, calculus. Woo, we loved calculus. Calculus 1, right? It's one of our favorites. I don't know, I liked it a lot. That's why I took it twice. No, just kidding. So the limit as s goes to 0 is of 1, and of 1 is just 1, right? They don't depend on s. So we can just take the limit as s goes to 0 of g of s, and we're going to actually break that limit out separately and call that limit kp. So this is what's called the position constant, and it's just the limit as s goes to 0 of g of s. So that's just the position constant. We'll talk about the naming. I'm not a huge fan of the naming, but it's used. So position constant kp. If kp is large, the steady state error will be small, right? So if kp is like 10 million, then 1 over 10 million and 1 is a small number. So the steady state error will be small if the position constant's large, and if the position constant's small, then we're going to have a steady state error of 1, and you can also have kp come out negative too, right? So that's another case you have to watch out for. So these are our cases for kp. Now, remember, G includes our controller and our plant. So that limit as s goes to 0 is going to be affected by what's in the controller and what's in the plant. And we can usually not change a lot about the plant. The idea of putting the controller on there is to make the plant do something that it wouldn't normally do. So the controller is there as like the external thing that we can change, and the plant's usually not very changeable. I mean, there's always some possibility you can change the plant, but usually your focus is changing the controller. All right, now, good. The form of g of s has implications for kp. G of s has a factor 1 over s to the n, where n is some non-negative integer. So let's look at this factor. 1 over s to the n. If n is 0, then it's 1 over s to the 0, or just 1 over 1, or just 1. That's why I say that g always has this factor in it, because you can always set n equal to 0, in which case it's just a factor of 1. Otherwise, these s's are things you can factor out of the denominator, right? These s's can be factored out of the denominator, and that is what we're looking at here, these factors of 1 over s. Since we're concerned about what happens to g when we take the limit as s goes to 0, this factor is of particular importance. So if there is an s you can factor out here, if s goes to 0, for instance, then that's going to make this fraction infinitely large, right? That's important. We're about to look at that. So if n is greater than 0, Kp is, so it's equal to the limit as s goes to 0 of g of s, it goes to infinity, right? So if n is even 1, if you even have one of these terms, then 1 over s goes to 0, 1 over 0 is infinitely large, right? So infinity is the position constant Kp. If you plug infinity in here for the steady state error, we get 1 over infinity, which is 0, right? So 0 steady state error. So if you even have one factor of 1 over s in your transfer function, you have a 0 steady state error if you have a step command, okay? So that was what we just discovered. We didn't solve for e explicitly then. All we needed to know is the command r and the number of integrators n in the forward path transfer function g of s. We call this the system type. So we call these, oh, I skipped this. So we call the transfer function 1 over s an integrator, okay? Which is the inverse of the transfer function s, which we call the differentiator. So if you look at integral of a function of time in the Laplace transform table, you'll see that it's just equivalent to having a 1 over s times that the Laplace transform of that function. And if you look at the derivative, you'll see that you have that factor of s that shows up. And we've already seen that one quite a bit in the system dynamics portion of the course. So let's focus on okay, this terminology. So if n is 0, we have 1 over 1, or just none of these 1 over s terms show up, so we have no integrators. If n is 1, we have 1 over s to the 1, so we have one integrator. If we have 1 over s squared, that's 2 integrators. Cubed is 3 integrators, etc. Okay, so we talk about like number of integrators, and it's going to be an important concept, number of integrators there. And what we do in the next paragraph here is we define another term for the number of integrators, which is called the system type. We needn't solve for e explicitly then. All we need to know is the command r and the number of integrators n in the forward path transfer function g of s. We call this the system type. So number of integrators is the system type. 0 integrators, type 0. 1 integrator, type 1. 2 integrators, type 2. Ooh, that was a bad joke in there. Did not say it, though. I'm so proud of myself. The steady state error for other commands and system type can be derived in the same manner. The results for the canonical inputs are shown in table 4.1. So let's take a look at this table. This table is a little bit more extensive than the one that's provided in the book. I think it's better than the one provided in the book. And I encourage you to use this table versus that table, but it's your call. And the table in the book is pretty good. It's similar. So there is a row for each of the sort of canonical inputs here. The unit step, the unit ramp, and then this unit parabola, we could call it. Okay? And for a type n system, we're going to look at the error constant and then the steady state error. This is the general formula. So if you have any system, type n, you can go to this table and you can look for a unit step, for a unit ramp, for a unit parabola, what the steady state error is going to be based on this column. Now, the type 0, type 1, type 2, what we're going to do is we're just going to evaluate what this type n column would look like if you have the information that it's a type 0 system or a type 1 system or type 2. Essentially, if you know how many integrators there are in your forward path transfer function in G. Okay? So we did this first row. Let's walk through it. We had the unit step as the command, right? We had Kp was our error constant. We call it the position constant, which is the limit as s goes to 0 of g of s. The steady state error we derived was 1 over 1 plus Kp. Okay? we can do a similar thing for a unit ramp function and for a unit parabola as well, and that's what these columns show. Kv is called the velocity constant, and Ka is called the acceleration constant. It's just because of this, it looks like position, velocity, acceleration, if you're integrating or differentiating, let's go the other way. And that we're familiar with that concept from dynamics, and that's why we call them position, acceleration, and velocity constants. So that's the name of them. I don't really care. The names are not important, really. I kind of think they're a little bit misleading because it doesn't have to be position. It can be any variable you're controlling. So yeah, or it's like it thinks in a mechanical way, which is okay, but we like to think of systems in a more general way. So we have these general formulas. We're going to apply it to a type 0 system, type 1, type 2. So let's go down the first row. We already did this. A type 0 system with 0 integrators. We find, so the error constant is Kp, and the steady state error is some finite value. We got to find out what Kp is in order to plug it in. So you have to actually use the formula for Kp here. If you have a unit step function as the command, in a type 0 system, there's some finite steady state error. We got to compute it. Okay, but if it's a type 1 system, like we saw, if there's even one integrator with a step input, type 1 system, one integrator, we're going to have an error constant that goes to infinity, right? And we saw that. So if there's one integrator, the error constant goes to infinity, which means that if Kp is infinity, 1 over infinity plus 1 is also 0. So this is 0. For a type 2 system, you just add another integrator in there. You don't add it. You include it. You include another integrator in there, you multiply, right? Add is a deceiving way to say it. So we're going to go to 0 error again. So let's do this row here. It turns out that the error constant, if you've got a ramp input, if we compute this error constant, look, there's an S that comes in. Okay, this Kv. That S is going to screw us up because it's going to cancel one of our integrators, right? It's going to cancel an integrator in G. So instead of having an error constant that's finite and steady state error of 0, or of some finite value, we're going to have an error constant of 0. Okay, that's bad news because if an error constant of 0, we're going to have a steady state error of infinity. So if you have a type 0 system, you have no integrator in your system, and you have a ramp command, you can't keep up with it, essentially. Like a steady state is just going to go off to infinity. So you can't keep up with your command. With type 1, you include one integrator. We get back to the finite situation where we have a Kv as the error constant. You got to compute from this definition here. And we can compute the steady state error as just taking 1 over Kv. Type 2, we have 2 integrators. Finally, we've canceled only one of our integrators with this S, and we're left with an infinite error constant and 0 steady state error. So type 2, 2 integrators, even with a ramp input, you got 0 steady state error, which is good. Now, if you go up to the parabola, once again, we've got 0 error constant, infinite, because you've got no integrators and you've got 2 s squares you needed to cancel and you didn't cancel them. So you got hosed there. Same with here, 0 and infinite. And then finally, once you go to 2 integrators, you cancel both of these s's. So Ka and 1 over Ka, exactly. Exactly. So that's our full table. So what this is like a shortcut to answer. So we're going to do, we'll do this example here. And we'll see how easy it is to do this using the table. So let a system have for a path transfer function, such and such, 4 commands, R1 being some scaling of the unit step function, R2 being some scaling of the unit ramp function, and R3 being some scaling of the unit parabola. What are the steady state errors? So let's evaluate this. First off, we've got to figure out what type system we have. So we need to find out what is the number of integrators. We can find that by looking at how many s's can we factor out of the denominator. So what do we have? 1. Just 1, right? You can't factor out any other s's from this. So it doesn't matter where that s showed up. It could have been s squared plus s. You could have factored out 1s, right? So once you factor out s, you have the number of integrators factored out. So that's there. So you got to do that factoring out first. So we have a 1 integrator. So we have a type 1 system.
If you can cancel s's from the numerator, do you have to do that first?
So pole zero cancellation is a little bit subtle, but for purposes of steady state error, yes, go ahead and cancel numerator and denominator. It's good whenever you have a transfer function, if there is one that cancels in there. It's good to just not cancel it, keep it there, because it's important information to someone who comes along that there was a pole zero cancellation that happened. So yeah, so type 1 system, and that's good. So now let's look at R1. So we have 2 times the unit step. Now we have a type 1 system. So we go to the table, we say type 1. So we're working in this column. We're going to work in this column for all 3 parts of the example, right? Because the system type is going to be the same for all 3 parts. What we're changing here is the row, the R, the step, or the command from step to ramp to parabolic. So good. So let's look at a type 1 system with a unit step. We have infinite error constant and 0 steady state error, right? So we do need to make sure that we take into account superposition, which says that if you multiply the input, remember the command here was unit step, not 2 times the unit step. So if you multiply the input by 2, you got to multiply the output by 2. And so we would have the steady state error be equal 2 times 0, which is just 0. This is fine in this case if we forgot about scaling, but we should be careful. R2 is e of infinity is equal to, so now we've got to go down to a ramp function. So R2 was 6 times t times the unit step, so we have a scaling of 6 here. And then we have an error constant kv, which is defined as this, and steady state error of 1 over kv. So steady state error is 1 over kv, where kv is equal to the limit as s goes to 0 of s, g of s. And we've got our g of s, so let's take that limit. The s cancels with this s, right? So then we're left with all the s's go away to 0, so all the s terms go to 0. We're left with 10 times 3 times 4 divided by 1 times 5. So we have 2 times 3 times 4 is 24, right? So we've got 24. So then so e of infinity equals 1 over, or not 1 over 24. Oh, we screwed up, right? We got a scale. We have a scale of 6, right? So we had 6 over kv was going to be our steady state error. So 6 over 24 or 1 over 4. Yeah. Good. R3 is going to be e of infinity equals. Now, this one's got a scaling of you got to be a little careful with this one because this one has a 1/2 out here, right? So 1/2, if you compare it to this one, 7. So you multiply 1/2 by 14, right, to get 7. So it's 14, but it's 14 times, what was the infinity? So in the end, it didn't really matter, the 14. 14 times infinity is just infinity, right? So that's all we got. Yes?
So is the error for R2 25%?
It's deceptive. It's actually in the units of whatever your command and your output are. So if your output is in meters per second, you're measuring the feedback in velocity. This is going to be in units meters per second. So the unit of your error is the same as the unit of your command and the same as the unit of your output. So you do have to be a little cautious about that. And you can have errors that are greater than 1. Like for instance, if we had put in instead of a 6 times a unit ramp, we put in like 100 times a unit ramp, this would come out to be greater than 1 over here. This error would be greater than 1. So it's actually an absolute value. It's not a percentage. Yeah.
So in that way then, if you're going back to the right? So if you say I want to move it 30 degrees, you could have move accidentally 61 degrees then.
Yeah. Yeah. So yeah, it could be over 100% error. Yeah, totally. Yeah. So yeah, it's actually like, so you get back, the error would be in, if you're doing it in radians, it would be in radians. Like that's what the error would be in. So, or if you did it in degrees, your error would be in degrees. So it's whatever units you're using for your output. So if you're measuring it in whatever unit you measure it in, then that's the unit that the error shows up in. Yeah. All right. Any questions? Any other questions? All right. Have fun tonight, guys. Maybe I'll see you out there.
Maybe. I advertise it, so maybe you'll see some.